Good morning everyone and welcome to my YouTube channel. So we are looking at the second part of microscopy, which is our resolution. So what is resolution? Resolution is simply defined as the ability of a microscope to be able to distinguish two very close points as separate. So get the difference. Resolution has to do with the ability of the lens to distinguish two very close points as separate. However, when we look at magnification, it is how large. So resolution is more like it determines the clarity. So at one point you might have these 2 points like this, but at a certain zoom, what begins to happen is that if the resolution is very poor, these 2 points might be looking as if you are just looking at one thing. So this is what we mean by resolution. So resolution is the ability of a microscope to distinguish 2 points as separate. So if 2 points are considered to be separate, or rather are seen to be separate under a microscope, that means to say you are looking at your resolution there. So it is the minimum distance where you can see 2 very close points to be separate. So when we look at our factors affecting resolution, number 1, we have the wavelength. So wavelength, this is an inverse relationship. If we have a longer wavelength, it means to say longer wavelength will produce lower resolution. Likewise, if we have short wavelength, then we will have higher resolution. So if we are to compare the colors of the rainbow, we have the RGB. So we have our RGB like that. So these are colors of the rainbow. You will realize to say red has got a longer wavelength, therefore the resolution it provides is less as compared to, let's say, a color such as blue. Blue has got a short wavelength as compared to red, therefore it has got the tendency of producing a higher resolution as compared to red. The other example of a short wavelength that we can talk about is if you compare the light microscope and the electron has got a better clarity, or rather a better resolution, as a result of the wavelength of an electron is very short. So therefore even the resolution is greater. So that is the relationship that is there. Other factors are what we call numerical aperture. So numerical aperture is simply defined as the microscope's ability to gather light. Therefore, the numerical aperture, simplified as NA, is given by the formula, the N, where N is the refractive index, then the sine of the angle, theta, like that. So this is how we find the numerical aperture. Now remember, the wavelength of a material determines the numerical aperture. So let's imagine this is our microscope. So what begins to happen is that as light is coming from here going up there, now the tendency of light is that when a medium is changed, such as when it passes through the slide, you can see that here what we just have here is air. So instead of the light rays bending so far, so what scientists will do is that they will apply immersion oil at this point. So by applying immersion oil at this point, what they begin to do is that they increase the refractive index, because the refractive index of oil is approximately somewhere 1.15, which is also, when we look at grass, it's 1.53. So by making it close, because this is made of grass and also we have the lenses are made of grass, so what we are doing there is that we want to make it compatible with the immersion oil so that light does not bend a lot, thereby increasing the numerical aperture, which is the ability of the microscope to gather light. So if the microscope gathers more light, that means to say there will be better clarity, which is in this case our resolution. So numerical aperture may be increased by applying immersion oil. By applying immersion oil, you directly increase the resolution. So sometimes some other books will tell you that the numerical aperture is 1.4, which is one of the recommended 1.4. So in other words, the grass might be somewhere the resolution of this, but all in all, you can just realize to say 1.4 is very close to this. So this is for glass. This is glass may take these values. Numerical aperture of the oil might be this. So by having a not numerical aperture, sorry, by having the refractive index being close like that, you now are able to achieve the light rays not to bend a lot away from the microscope. So therefore you increase the numerical aperture, and increasing the numerical aperture increases the light gathering ability of the microscope. So don't get it wrong. 1.15 and 1.53, this is the refractive index of glass. Numerical aperture might be 1.4. So now let's look at the equation connecting the two, the numerical aperture and the resolution. So the resolution, the symbol is D. So the resolution, the symbol is D, should be equal to, so we have our 0.5 wavelength over the numerical aperture like that. So now we have the situation. Other books will tell you that 0.16 lambda over the numerical aperture, but for this video we are going to use this constant 0.5 wavelength over the numerical aperture. So we know that the numerical aperture, we have said that it is n sine of theta. So let us be able to solve a question where D is the resolution or resolving power. Let's say we have this question: a microscope uses the light of wavelength 550. The numerical aperture is this and the objective lens is this. So the numerical aperture of the objective lens, let's say, is 2. So what are we going to do? So we know, let's say we are finding the resolution. Resolution is equal to 0.5 using this constant over our numerical aperture like that. So it will give us, we have a 0.5 times our wavelength. So our wavelength is equal to 550 nanometers. Then we divide this by a 2. So by dividing by a 2, we can divide a 2 in here. So it will be a 2, remainder 1. 15 divided by 2 gives us 7, remainder 1. 10 divided by 2 gives us 5 nanometers. So what we are going to have is a 0.5 times a 275 nanometers. This is what we are remaining with. So we are going to have 0.5 is the same as 1 over 2 times 275 nanometers. So this gives you a value of, let's divide. So 2 into 2 is 1. 7 divided by 2 gives us a 3. Remainder 1. 15 divided by 2 gives us a 7. Remainder 1. When we add a 0, 10 divided by 2 gives us 0.5. So we have the resolution of 137.5 nanometers. So this is our resolution, which is the minimum distance upon which two objects can be seen to be separate. So that is how we do that. So let's say we have a problem like this. First, the microscope uses air and refractive index is equal to 1 as a medium. The half angle of the light cone entering the objective lens is the sine of 30. The wavelength of light used is this. First, let's find our numerical aperture. So we know that the numerical aperture is equal to n sine of our theta like that. Now we know to say n, which is our refractive index, is 1. Then we have the sine of our 30 degrees. We know that the sine of 30 degrees is equal to 1 over 2 from trigonometry, which is 1 over 2 is the same as a 0.5 5 like that. So we can be able to say 1, where there is the sign of theta, we put 0.5 like that. So our numerical aperture is equal to a 0.5 like that. So we have found our numerical aperture. Let's find our resolution using D should be equal to, we have a 0.5 wavelength over the numerical aperture like that. So we have our D should be equal to 0.5. The refractive index we have been given is a 600 nanometers over our numerical aperture, which is something that we have found. It is a 0.5 like. So when we get this, to find the resolution, we are going to find that our resolution should be equal to this 0.5 cancel. So our resolution is a 0. Not 0 point, we have just a 600 nanometers. So depends with the instruction. Sometimes they might ask you to use this constant as per calculations. So you can even use this, though the answer will be different. So it depends on the microscope that you're using. For the sake of the exam, they'll give you which constants they want you to use, or whatever you will be taught by your lecturer, that is the value that you will use. So that is how we do resolution problems. Thank you very much for watching. Hope you would like, subscribe, and share for more.